Okay, afternoon. Okay, so this week going to add in time into our spatial and aspatial relational model. The first half of the lecture is a bit of one of my flights of fancy. We're going to explore basically the domain of time. What is time? Yeah, well, we'll see. Yeah, maybe a bit the sort of domain of time. And then the second part about is the hardcore stuff about how time is integrated into databases and GIS. This is just introductory slide, obviously. So, you know, the general argument for GIS is that everything happens somewhere. Well, everything also happens sometime. So everything happens somewhere and at some time, and that time is a common variable or in many different types of applications. So moving vehicles in a transport system, dispersal of pollutants, blah, 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 blah. Yeah, changing patterns in crime. Time is important, especially when you're trying to predict the future, because if you don't understand how things have operated in the past, then it's very difficult to predict the future, although Brexit and the recent American election has shown that the past is not always the key to the future, although I'm sure there are a lot of clues and things in the past information that can tell us about what happened in those two events. Clearly the standard prediction methods didn't give the desired result. Anyway, that's a sort of an aside. And clearly time has always been very important very important component of geographical data analysis and visualization. It's always been there. Has anybody not seen this picture? Everybody knows this. Charles Minard's, it's probably one of the most famous infographics there is. The advance and then retreat from Paris, and in particular in relation to time. On the bottom axis, we've got the temperature on the march back from Paris. Here's the size of the line is proportional to the amount of soldiers, and we can see, and the idea is that you can see how when the temperature drops, the effects on the army size are quite great. So time always been a component in geography. So, as I say, contents. What is time? Then look at various temporal scales, and then how time is represented in database management systems through data types, data models, and temporal relationships and time. And then finally wrap off with a little tour of the various tools and things that are available in ArcGIS. And of course, that's not a comprehensive list of spatial temporal analysis techniques. Many exist outside of ArcGIS, but I just took up the ones in ArcGIS as sort of an example of the sorts of analyses that are supported. So we start off with, what is time? Yes. So the first thing I want you to realize, understand, is that how people understand time has changed through time. So if we go back to the ancient Greeks, and I'm no expert on the history of all this, but Aristotle talked about time in connection with motion. Without motion, you could not have time. If everything was stationary, the concept of time is no longer valid. That was the argument. Without that time is effectively motion or linked to motion. And of course, the Greek thought lasted throughout most of recorded history. However, come the sort of 17th century, Newtonian physics provided us with a mathematical, to a certain extent, relationship with time, with space. Well, in fact, it separated time and space. So in Newtonian physics, I'm not an expert on this, you've got time is regarded as a totally separate dimension to space. Yep. You do things that go on in space, and time is just totally separate from that. It's a dimension in its own right. And that idea probably maintained in science for up until Einstein. Nevertheless, in the late 19th century, early 20th century, there was a movement that it's a sort of general social movement or movement of ideas that started to regard time as not a separate dimension from space, but an integral, that it was another dimension just like space was another dimension. So this is linked with the literature. So there's a very famous book written by an English clergyman, as in many great books are written by English clergymen seemingly, called Flatland in 1888, A Romance of Many Dimensions by a Square, which is the story of flat shapes living in a flat world who meet a three-dimensional sphere one day who intersects with their flat world. And it's about what it is it's a story about the realization that what you observe around you and how you experience the world is not the same as the reality of what the world necessarily is. So the argument would be, okay, in Flatland, two-dimensional things have no concept of the third dimension of space. Maybe we as three-dimensional beings just can't, in a similar way, can't interact with the dimension of time like two-dimensional creatures couldn't interact with the third dimension of space, so verticality. And it also comes out in this sort of idea that space and time are interconnected is linked to the sort of rise of spiritualism and in sort of religious or quasi-religious circles, the fact that spirits existed out of time, etc., etc. Also, it's linked to the sort of cubism and expressionist periods of art. It's this breakdown of the solidity of how you understand the world. The world is not, there's a hidden world, it's more complex than what we actually experience. Then come 1908, the great revolution of Einstein, relativity, and Einstein brought space and time together into a single integrated model of space and time where they are connected, related, but they are different things. So we've had this change in sort of conceptual understanding of what time is through time. So our understanding of time now may, of course, not be the same as in the future. So one of the fundamental things we don't actually know is whether there's a beginning and an end of time. We don't know. Okay, presently we believe the universe started in a Big Bang. I think that's generally accepted by most cosmologists, although there is an argument that the universe remains as a steady state. So we think the universe started, or our time started at one point. The universe is presently expanding. The evidence suggests that the rate of expansion is increasing through time. So it looks like we're heading for sort of a heat death of the universe. And if we think of time as motion, maybe that's where time stops, where motion stops or interaction stops. Who knows? So we don't know whether time has a start. We don't know whether it has an end. We think it has a start. We don't know whether it has an end. Of course, if the universe collapses again, then perhaps we collapse back to a singularity and time stops again. Anyway, so we don't know whether it has a start. We have this idea from Aristotle, and quite very reasonable idea, that time is related to change. Without change, how can we measure time? How the concept of time breaks down if we think of things not changing. So just a quick slide to show some of the things that might change through time. So things come in and out of existence. They begin, we're born, we live, we die. An earthquake occurs, it begins, it shoots out, it lasts for so many minutes, and then it's gone. So things come into existence and they end. But things can do more complex things. They can split and merge in time. So this is particularly relevant to my research. I'm interested in species and speciation, how new species evolve. That is the product of an ancestral species breaking apart into two separate species through time. Interestingly, two separate species sometimes can come together and join again and become one species again, or at least. So splitting and coalescing of things. Think of countries. Countries come into being, they exist for a while, then they break apart into other geographical units. So a country or an administrative unit may also split or coalesce through time. We've got simple changes in attributes through time. So this is abundance record through time of this particular duck, whatever that is. Anisactua, I'm not expert on my ducks, but the number of these ducks observed at any particular location through time, the number value of the attribute change through time. There is also change in location through things. So one thing that's moving or flowing across the land, the landscape. So here's Hurricane Andrew, 1992. Here's the track of the centre of the hurricane. Obviously, the hurricane itself may grow, contract in size as well. So we've got changes in shape as well as changes in location. And then we've got the tempo of change as well. Things happen quickly, things happen slowly, things happen periodically. So there's all that aspect of change as well. Change, I'm trying to remember my sort of narrative in my head here. Change is the result of events happen. So events are change by their very nature, but they also knock on and have effects in existence. So we tend to measure things in time, or conceptually think of events in time. We think of something happening, an earthquake happening, a traffic jam happening. So events, and then these events may have subsequent causal effects. So time is without time we can't have causality as well. So we need an event, some kind of event happens, and the arrow of time means we have various causes, and that results in this case in an effect. So time is required for causality. That's the thing. Without time we have no causality, we have no cause and effect. We mostly experience time as linear. You know, a minute is a minute, whether it's today, whether it's tomorrow, whether it's next week. In most of our, well, we'll talk about when life doesn't feel like linear, but linearity seems to be the norm for time. It carries on, it progresses in a standardized rate. It's not like time speeds up and slows down, but certainly when we measure it with a clock, except if we're going at speeds of light and things like that, and that's where Einstein, obviously general relativity comes in. It's at these extreme times. So time is generally linear from the past to the present and into the future. It's also unidirectional in respect of everything, almost everything we know about, in that we can't go back in time. Past events can't have direct influence on future events. They may have indirect influence. And of course, with that directionality, linearity in time, but that doesn't mean that things are necessarily changing in a linear fashion simply with time. So clearly we have trends, long-term trends, due to various drivers of the systems that we're interested in. So this is data from the Living Planet Index, which is a sort of global measure of the biodiversity across the whole planet. And we can see through time, 1978, something happens in the late 70s. The bite rate, the overall measure of biodiversity throughout since 1970 has generally been a trajectory downwards in the quality of the direction. So we've got directional change through time. In this case, relatively linear by the look of it. This is actually quite frightening, some of the newspaper reports recently about 60% of the population of various species having been wiped out in the last decade. I mean, that's seriously scary stuff at a personal level. All right, not only do things have trends, long-term trends, also time, we have these cycles. Many systems exhibit cycling. So this is the Southern Oscillation Index, which is basically a measure of sea temperatures in the Pacific, which is basically El Nino, El Nino. So the climate, it's a roughly, I think, every 3 years, 4 years, the El Nino cycle. But we can see the La Nina cycle here, and the opposite, the El Nino here. And we can see that we've got quite a strong cyclic pattern there over the scales of decades. I think the actual cycle is roughly 3 to 4 years on the El Nino. But clearly that's just one example of a cycle, and cycles can occur at lots of different temporal scales. So human movements, maybe we've got cyclic movements on a day basis, commuting to work, home, etc., on a weekly basis, going to work, having a weekend, obviously, on a yearly basis, maybe to do with things like seasonal employment or things like that. So there are cycles at that scale. There are cycles maybe at the yearly scales. For example, the Arctic hare lynx predator-prey interaction. Basically, the populations of lynx and hare do alternate every 3 years. And then we've got things going on at much longer time scales, things like ice ages and things like that. So ice ages are driven by various things. One of the most important is what's called the Milankovitch cycles, and these are eccentricities in the Earth's orbit which control how close the Earth is to the Sun. And there are various ones of these cycles. There's one at 100,000 years and one at 413,000 years. So you've got all these cyclic things going on at different temporal scales as well. And this is a diagram. This is the history of the Earth over the last 500 million years. It's the temperature of the Earth. And when we sort of zoom out, suddenly we don't have a linear trend. We don't have a cyclic trend. We've got something that's a mixture of a whole load of different things, unsurprisingly, because different things are occurring at different points in time, at different spatial scales that result in different amounts of cyclicity and things like that. So at this point, when we've got a time series that's something like that, clearly we've got cyclic behavior visible in certain areas of the graph at different scales. Now, do those different scales represent different means of measurement, things like that? We've got certainly areas where we've got linear trends, but overall, it's not a cyclic pattern, it's not a linear pattern, so it's a complex pattern that's the product of many, many different drivers. One of the issues with dealing with data and time is this problem of information decay. Everything decays in time. It's going to be one of those kind of gloomy lessons, lectures where we all die at the end. But data, so when I go out, so I'm interested in the evolution of fish as the trans-Mexican volcanic belt, a volcanic mountain range across Mexico rose. It took roughly 15 million years for this mountain range to rise, and the fish got dragged up with it, and the rivers changed direction, and the fish started evolving. But one of the problems I have is that I can get quite a lot of information on what happened, say, 10,000 years ago or 1,000 years ago. I can get lots of information about what's happening now, what the present situation is. But when I'm going back to 1 million years ago, or 2 million years ago, 3 million years ago, the amount of information that's stored in the landscape, so to speak, that I can query and investigate to find answers to my problems, as in, when did this river change from flowing that way to that way, gets sparser and sparser and sparser. Simply because either the information is not visible in the landscape because it's been eroded away by erosion, or it's been built upon by, a city's been built on top of an important bit of geological evidence. How could they possibly do such a thing? Or that nobody's gone out and actually done the survey to collect it. So there's lots of different reasons why, as you move back in time, the information content becomes less and less, and the information availability becomes less and less. And while you may be thinking, oh God, well, he's working in millions of years, that doesn't matter to me. But if you're dealing with even socio-economic data, as you go back in decades, a few decades, particularly before the computer era, the quality of the information and how available it is starts to drop off. So there's a real problem with this information decay through time when you're dealing with historical information. The World, this is a great book. I love this book. It's a bit old. I think it was written in the 1960s or early 70s. And it is about the story, it says what it's about, the making of the English language. It's, if you go and walk across through the English landscape, the landscape that you walk through is a product of multiple events in history and in time. And it is what we call a palimpsest. Now, a palimpsest comes from, the word palimpsest comes from ancient Egyptian, or the interpretation of Egyptian hieroglyphics and whatever the roles of a papyrus. And basically, a bit of papyrus would be, something would be written on it. Papyrus was a valuable resource. So rather than throw that piece of paper away, or that piece of papyrus away, it would be used for something else as well. So that the text on a piece of papyrus may have been composed over many years by many different scribes, annotated, etc., etc. So the content of the document is a product, or is the result of many authors changing the text, amending it through time. And a landscape is just that. This landscape here, we're looking at some kind of, it's a scarp topography, isn't it? Scarp vale topography. Could be in northern England. Probably looks more like northern England, but it could be somewhere in the Downs here. But here we've got a path running along the top of the ridgeway, or the ridge here. This may well be a prehistoric pathway. This is, so if you go down to Guildford, you've got the Hog's Back Ridge. I don't know whether you're familiar with it. Have a look on a map. It's a big ridge that sits there and runs quite a large along a large section of southern England. And that was where the roads were. Now our roads are down in the valleys because it's relatively flat. In prehistoric times, the roads were built on the hilltops because they were drier and easier to walk across. So we've got potentially an ancient footpath running through here. We've maybe got these fields down here, may well have been enclosed in the enclosures in the 18th century, 17th century. Then there was maybe the clearing of upper lands and the instigation of hill farming and things like that. So when we look at the landscape, what we see is a palimpsest, a mixture of different times, events in time. This is a product of many different events, scenarios through time. And we can make maps of this kind of thing. This is called a historic landscape character map. And these are being produced by various people. This one's from historiclandscape.co.uk. So this is a company that is subcontracted by councils and people like that, planning departments, to understand landscapes. And basically the idea here is that a landscape reflects the time, or the times in which, the dominant times in which that landscape was created. So here we have, in this is a historic village of Sixpenny Hadley, which is a wonderful name, which is a medieval village surrounded by 18th, 19th century fields. So we've got some of this landscape as the product of the pre-1800 historic land use around commons. So we've got sort of open field, common environments. Then we've got the enclosures, the enclosing of the fields. We've got medieval villages. So we can characterize a landscape by what we can think of its typical age. There was a wonderful sort of one of these BuzzFeed maps that I was trying to find the other day, and I couldn't find it, which has the whole world, and it says where do you, or what time period do you live, where you are in the world. So most of Western Europe, we're living in the now, but say Australia and New Zealand, they were reckoned were living in the 1950s, and most of or let's say sort of the advanced Asia, Shanghai and things are living in the future. It was quite a good, I quite liked it. It was a nice sort of humorous take on this. Now, we know kind of what the world is like now. We've got a reasonably good idea. Now, one of the problems with history, with time, if we both look into the future and the past, is that there's often many, as I say, as it says here, alternate realities that we can consider. So these are climate simulation models, and it's basically each line on the graph is the output of one of these climate simulation models. And we can see that as we move from the present into the future, where we're doing the predictions, there are lots of alternate realities that these models can predict. So we've got a problem, what Lester maybe called, what Lester returned to as branching time, whereby at this point we know where we are, we're in agreement, but then these models, they start to diverge. So we've got alternate realities that we could follow into the future. And we can do exactly the same thing into the past, which is a problem I have with my Mexican data, in that I've got all this partial information about the history of rivers, volcanoes, and things like that. But there are probably several different ways that that information could be put together to provide a coherent story for what we see today. So how do I encode in my database and my database models these alternative possible histories that might exist, or my data may support. And that's just showing those same, this is a land use modeling example of pretty much the same thing, where you've got alternative models under different scenarios showing the landscape change. All right, so I said time is linear, time is cyclic, but time is also a human experience, or not just a human experience, it's an experience of living creatures. So it's not impossible that chronological time is not actually what you're necessarily interested in. So bear that in mind. So if you're a commuter and you're sitting on a bus in a traffic jam, time slows down and it all just takes forever. Whereas if you're in a rush and you're desperate to get somewhere, time just flies. So there's a psychological aspect to time to bear in mind. So you may work in a domain where you have to think, well, is it the actual time that's important to somebody here, or is it the perceived time that they experience? So that's more of a psychological thing, but it's something to bear in mind, because I'm just, as I say, putting my hand and trying to circle in what the domain of what time is. Now, non-biologists probably aren't aware of this. Obviously, it's not just humans that experience time, but animals do as well. And interestingly to me, as a biologist or biogeographer, is that the size of the animal and its metabolic rate determines how it experiences time. Why is it difficult to swat a housefly? Is it because we reckon it experiences the world almost 7 times faster than we do? So as I try and swat it with my hand as fast as possible, it's like this for the fly. You know, off it goes. So the way animals and experience and interact with the environment may also depend on their internal clocks and how they experience the world. So if you're interested in animals and their behavior, how does the animal experience time? Psychology, here's another bit of psychology, marathon running. Another great graph. So this is, I don't know which marathon this is, it doesn't really matter. But if we look at this graph, this is the number of finishers and the time period. What we get is a nice, well, it looks like a reasonably good, not quite a normal distribution, but importantly, 4-hour peak, 3-hour peak, 5-hour peak, 4.5-hour peak here, and then there's these minimum dips. So psychologically, people want to finish under the hour, under the half hour, these arbitrary units of time that they have in their head, and that can have a really large effect on behavior. Also notice who's responsible for most of this behavior. It's the men. The women seem to be a bit more relaxed about this. It's not that they're not It's not relevant, but it's clearly, for men, it seems to be much more important. So time may vary by gender as well, and how you experience and deal and what your reactions to time are, your psychological reactions to time. Very last one, I think, on what is time. Okay, highly unlikely to need to consider time travel, but think of a GIS of films, the events, the timelines of films that involve time travel. It is possible to envisage a time travel as needing to be considered in a GIS context. Probably rather unlikely, but you know, it is possible. All right. Space and time. So space and time go together like, I don't know, strawberries and cream, maybe not. You can't, as I say, these concepts of time right from the beginning had space and time intimately linked. And this is true across multiple, in fact, I think just it's almost, let's say, is it geography's rule number 2, the law of geography, so the Tobler's first law of geography, things that are closer to each other are more similar to each other. Well, here's another potential law of geography. I've just thought of this off the top of my head, but things that are further away take longer to interact with each other. It's a sort of part extension of Tobler's argument. So, not surprisingly, this is boreal forest, so a conifer forest, and it's the relationship, some of the processes that go on in the structure of the forest, the structure and the processes in the forest, and the spatiotemporal scale. So here's the spatial scale in log kilometers. So each unit is 2, is a change of an order of 10. And here we've got time in years. And not surprisingly, really, when you think about it, things that are relatively local in space are also local in time, generally. But as you get into larger spatial scales in this direction, the temporal component of it also increases. And you can draw these I actually collect these diagrams. If anybody sees any of them, then do send them to me, because I have a collection of them. And we can clearly see that studies and disciplines study different spatial scales, but they're also often studying different temporal scales as well. If anybody's looking for a project one day when you're thinking about your dissertations, I'd like somebody to digitize all these diagrams and then overlay them in a GIS, and to look for, are there particular spatial and temporal scales in which our conceptual models change? The other thing is, can you take the data for something like a boreal forest, and can you extract these similar kinds of these conceptual drawings out of the data for an actual forest? So if anybody's interested in space-time exploration, there's an idea. All right, that's my ramble on what is time. And ultimately, it doesn't matter for most of us. I think it's interesting because I think there are lots of things there that a lot of people never have thought about. And I find it interesting. I'm interested in time. But from an IP perspective, it doesn't really matter. But from a domain perspective, it's very important. If the psychology of time is important, then you need to consider it. But that's the domain area. But what are important from a GIS perspective, from a hard IT perspective, is things like, how is time measured, its accuracy, its precision, and the spatial scales that we use. And how is time represented in computers? How do we store time? Temporal, well, we probably need some kind of data type. We need to be able to undertake queries. We need to be able to potentially specify relationships in time, managing these changes that I briefly talked about in the entity's existence, attributes, location, relationships through time. We also need to consider changes in the database state through time. So that is, okay, today the database has these amount of records in, tomorrow there'll be some more records, but some of those records will relate to time yesterday or before. So there's a difference between the time the data is in the database versus the time that the database facts are temporally referenced. And although I don't cover this, you always end up this uncertainty. So when I went over to talk to the council people over the road, I was looking at some maps they were making of, they were actually time maps. They were time isochrone maps, yeah? So maps of how long it takes, travel time maps. And because apparently the people who are firemen, or certainly chief firemen, have to live within 20 minutes travel time of the fire station that they're responsible for. And we were they produced these maps to show where people had to live, basically, if they were going to be chief fire officers or whatever. And we just got into a discussion of uncertainty. How good were the models? Plus or minus 20 minutes. Yeah, there were no figures, I pointed out. There was no measure. There was no measure of uncertainty on the map. And yeah, we generally had a little chat and just agreed it was important, but it's been one of these topics that's always raised in GIS ever since I was a master's student. And there are lots of techniques for uncertainty, but it's still something that's not being seriously dealt with, I think. Anyway, all right, so how are we doing? Let's just do measuring time. Right, how do we measure time? Some kind of calendar. This is the, well, I can't remember what it's called. I've actually seen it in the museum in Mexico City. It's one of the, Naztec, not Naztec, one of these historic calendars. Okay, so first of all, to measure time, we need some kind of unit, unsurprisingly. Time is continuous, but to measure something, we've got to divide it into some type of unit, which may be of uniform, but maybe variable length. So we have to take this continuum, divide it into some kind of units. And of course, the units that we usually use, seconds, days, minutes, months, but there are other units that we can come on. So certainly for biological data, season is a really important time period, summer, winter, autumn. We've also got things like historical periods and things like that. And whatever system you're working in, the smallest unit of time is generally called the chronon. According to Paquette, 2002. That Paquette paper is up on the additional reading. So how do we measure time? Okay, so we need some kind of unit, and we need something that provides us with a measurement, measures those units. So clearly, clocks of various kinds. Clocks are things that measure time, basically. And the two types of clocks. We've got what you normally think of as a clock that directly measures the change in time, whether it be through the dripping of water through a water clock. You fill it up, each division is maybe an hour, and the amount as the water drops through, it records time. Similar idea with a candle, and then we have obviously more conventional clocks. So we can directly measure present time. That's great. We can't directly measure historical time unless somebody had a clock and was recording that time at a particular time. And that clock we know the calibration of that clock, how that clock was set in the past, because it might be set to a different time scale than we're present in. So the second type of clock is not what you could call a direct clock, but an indirect clock, a proxy clock. And this is usually used for deeper time. So here, you've got, this is the radiocarbon dating calibration time. So if we want to, so radiocarbon dating allows us to go back to about 20,000 years ago, and basically the concentration of the radioactive carbon-14 declines through time. So that gives us a proxy measurement for, or an estimate of how long ago say a piece of wood was alive. Okay, because of the concentration, how the concentration of carbon-14 has changed. Notice this is not a straight line, and that's because the amount of carbon-14 in the atmosphere changes depending on the environmental state of the Earth at any particular time. So you have to, basically, Earth temperature affects the amount of carbon-14 being fixed, as the way I understand it. I'm not an expert on this. Hence the non-smooth line. So you have a degree of error and a bit of calibration required in your radiocarbon dates. Here's another alternative. This is another example of a different type of clock. This is using ammonite fossils for plots. Sorry about the emphasis on geological data. It's just to say this what I'm interested in. But so here, the various ammonite species of ammonites are only found in particular layers of rock, and it allows us to identify and date the various rock levels. And in this case, there is no absolute time on this scale whatsoever. So we don't know whether, okay, we're in the lower greensand here, which is in the Carboniferous just before the dinosaurs got bonked on the head. But so we know what the dates of the lower greensand in, but within this unit, all we know is that if we find this fossil in a particular rock unit, we know we're in the whatever unit of this is, and we know that we're younger than the units with these ones in and older than the units that these ones in, but we don't have an absolute time for that unit. We have a sort of sequential time. We have an ordered time. So temporal scales. Have you, wasn't sure whether you'd had a lecture on levels of measurement yet? Ordinal, nominal, I would have thought so, yeah. Ordinal, nominal ratio? Is that yes? Yeah. Okay, maybe not, can't remember them exactly. But we can think of, so there's these levels of measurement, nominal, which is basically categories, ordinal, ordered sets of characters, interval, which is an absolute measurement but from an arbitrary 0 point, and then you've got absolute scales which have a real 0 point. Okay, so there's different types of measurements, and I'll give you some more examples of these in due course. And I think you can have temporal scales in any of these that are absolute, interval, or ordinal. So, for example, you could have, probably the most normal thing we have is we work every day today is an example of interval time, okay? The time on our clock, the phone, it's got a date, it's got a time. That is from time 0, which was whenever that was, arbitrarily, some guy in the Middle East a long time ago had an unfortunate death. So that's basically where the 0 is. That's relatively arbitrary because it could have been obviously any point in time we could have taken as the arbitrary 0 point for our scale. So our present day time, everyday time, is an example of interval time. What does that mean? Well, okay, so it's now 2017. So let's say if we doubled, or we multiplied the year by 2, 4,000, so it's now 4,034. 4,034 is not double 2017. Now, it is as a number, but as a date, it's not. It's a meaningless statement, yeah? You didn't say, don't look convinced. Yeah, it's a meaningless statement. And that's the difference between an interval time period and an absolute time period. An absolute time would have a real 0, and you could say that double the time is really double the time. So the only time scale that would have an absolute 0, presuming the Big Bang is real, would be the cosmological time scale starting with the date of the Big Bang. So that would be an example of an absolute time scale. Chances of you needing an absolute time scale for GIS is pretty low. But imagine you were dealing with the geography of different planets, which is, people do. You know, it's not that unusual. One student last year was doing GIS geology of Mars. You know, it's perfectly possible. So if we're comparing things at cosmological scales, at the scales of planets, that may well be important. Most of what we're interested in is obviously interval time, relatively modern times. I have to deal with an awful lot of ordinal time, in which I know roughly the ranking. I know something is older than something else. I may well know it's between 100 million years and 90 million years, but I don't know where it is within that time scale. So in that case, the ordinal time, we're talking about units of time that are ordered, so geological examples are examples of ordinal time. Nominal time I thought was quite hard on. So the only thing I could think of for nominal time was basically you knew that you have a group of set of values and you know that certain ones of them were collected at certain times, but you don't know the relationships between those groups of observations that you know are collected at the same times and other groups of observations. So you know this one was taken at time 1 and this one was taken at time 2, but you don't know whether time 1 was before or after time 2. Maybe that's part of your inference analysis that you're trying to actually do, is to order things that you know go together and happened at the same time to temporal units. All right, just finished. We'll just do the scales and then we'll have a break. Okay, so present day time. Time at the moment we record is under what's called coordinated universal time. That is world time. This is the agreed standard for world time, established in 1961 by the International Radio Consultative Committee, and it is the successor of GMT, Greenwich Mean Time. Greenwich Mean Time doesn't exist anymore, despite the fact we talk about it all the time. It's actually UTC. What is it? Well, it's the weighted signal of several atomic clocks. It's probably still on the iPlayer, but if you're interested, there's a series on BBC 4 about measurement. Wonderful entertainment of an evening. It's a series of 3 programs, and they go through how fundamental measurements and units of measurement have been decided. So they tell you what the meter is. Who knows what a meter is? Yeah. The metal bar, but why is the metal bar as long as it is? It's 1/10,000th the distance between the North and South Pole. That's how they decided what a meter was. So it's not the length of the bar. The bar is just an approximation of what that value actually is. Anyway, so, but they did the units, and they had one on time, and they had one on weight and things like that. And it's really, I thought it was absolutely fascinating. Anyway, so several weighted value of several atomic clocks, one of which I think is just down the road in Twickenham, if I remember correctly, one of these atomic clocks. Then that's how we measure time. But one of the problems we have is that the ticks of the clock and the rotation of the Earth, which is how we experience time, we're interested in as much rotation of the Earth as we are in actual milliseconds or something like that. So there's a mismatch between the atomic clocks and the rotation of the Earth. So every once in a while, every so many years, they have to do things like add leap milliseconds and things to adjust for the rotation so that the atomic clocks are in tune with the rotation of the Earth. And then probably starting to get to actually something relevant to most of you is that, of course, the world is divided and organized into these time zones. And these are political time zones. These are not. So that here we are in the UK. We're on UTC 00, so 00. And as we go round the Earth, we go, I never remember which, oh, that's North America. I thought that's GMT -7. So as we go west round the Earth, the time zones and the time goes negative. Yep. So it's now, what is it? It's now nearly 3 o'clock in the United Kingdom, so it is 10 to 10 in North Carolina at the moment, 5 hours behind us. Okay, the time, the absolute time is exactly the same, but the time of the day and experience that we're having, it clearly changes. These divisions, as we can see, they're not straight lines. They are determined by country boundaries and things like this. So large countries will have maybe 2 or 3 time zones, 4 time zones. Small countries have 1 zone. So you can see the US here, we have Eastern time, we have Central time, and then we have Western or Mountain. I can never remember which one's Mountain time. Is that the middle one? Well, this green one's Mountain time, and then there's Western time. So there's 4 hours across the US. Some countries, big countries, I think India is one, have made themselves one large time zone because it's easier for management. So there are times, so there are time recorded. So if you've got somebody recording a time at 10:26 and they're in North Carolina, you have to think, is that local 10:26 or is that UTC 10:26? So decide which one. As you go back in time, presently we have a calendar which we're reasonably happy with. I mean, we know what the calendar is, but that calendar hasn't existed through time. It was, if I remember correctly, it was changed in the sort of late Middle Ages. I think about probably between 1500 and 1700, I'm no expert. But bear this in mind, if you're interested in historical documents, and the scale of days is important, and if you're tracking events, historical events, it may well be a day or two may make a huge difference. You have to bear in mind, was the date recorded using the modern Julian date or possibly the Gregorian calendar in the past? So you can see that there's 11 days difference in 1700, depending on whether you're using the Julian date or the Gregorian date. So that can make a significant difference to any analysis that you undertake. The fact that you've got 11 days difference between potentially different data sets. Oh, while I'm on that slide, there's a great, I love Wikipedia. I know other academics absolutely hate it. I'm a lover of Wikipedia, but I take everything in it with a pinch of salt. Don't believe it, but it's a great first place to go. They have a wonderful list of which countries were using which calendars at which points in time, and it is incredibly complicated. So if you're integrating data across Europe in this sort of historical period, maybe between 1500 and 1800, you've got potentially a huge amount of problems with different dates and calendars, or different calendars in different places at different times. Oh, that's just the international chronographical chart, just to show you an example of the interval time periods. I use this quite a lot myself. So we've got obviously these large scale, the eons, we've got the divided into subunits, and we can see that we've got a start and a stop date for these various rock units. So we know that the Norian period of the Upper Triassic was between 228 and 205 million years ago. Now that's great, but this is a global chart, and it's kind of averaging the change across the whole globe. But when you look, if you go to a geologist and you talk to them, now this Norian period may seem to exist for different lengths of time in different places across the planet. So while this diagram is a sort of global average temporal scale, when it comes down to the nitty-gritty of what's happening here, it may be several million years difference, tens of million years of difference between what you would think of the typical, say, environment in the Norian versus the Retian slightly later. It's a good place to stop. 5 past, and we'll get into what goes on inside the machine. Great.